In this video, we will talk about force in physics. So what's a force? A force will actually push or pull on an object so that the object accelerates. A force will push or pull on an object so that the object accelerates. Okay, so how do we denote force in physics? So we will say force is just a letter F with a head on it. Okay, now by looking at this notation here, you can see that a force is a vector because a force has both direction and magnitude. Now think about that. When you apply force on an object, right, then object is going to move and it's going to accelerate. Of course, it will move or accelerate in the direction, right? It could be going up and down, it could be going left or right, right? If it's just gonna stay the same, then it's not moving, or even if it's moving at a constant velocity, there's no force. So force is a vector. Okay, so another thing is that, right, a constant force applied on an object will make the object move at a constant acceleration. Okay, we can talk about this later in the video. Okay, so now, like I just mentioned, force, when a force applied to an object, the object is moving at accelerations. So when there's no acceleration, let's say the object is not accelerating, right? What does it mean? It means the net force, we call this net force like this, right? With a subscript net, is 0. What does it mean by net force? Okay, so net force is basically the sum of all the forces acting on the object. So we can write it like this. So the net force, right, is equal to, let's say, the first force, right, plus the second force, plus the third force, plus the fourth force, plus, okay, all the other forces. Okay, let's say we have that many forces, okay? Now, what does it mean, really? Okay, now let's look at an example, right? Let's say there's an object here. Let's say a point is the object. So let's say this one here. So this is the object here. And you have a force acting upward like this. Okay, so that, okay, let me make it clear. Okay, so here, like this, right? And then you have a force acting downward like this. Right? You have a force acting to the right like this. You have a force acting to the left like this. Okay, so let's say this is the first force, right? Force 1. And this one here is force 2. Right? This one here is force 3. This one here is force 4. The fourth force, okay? So there are 4 forces in total acting on this object here, okay? Let's say there are only 4 forces acting on this object. That's an example here. So if we add all these 4 forces together, and it's equal to 0, then the net force is 0. Okay, let's see, right? How, like, if we look at this, right? Apparently, all these forces have the same magnitude, okay? So here, all forces have the same magnitude. Okay, and of course, right, they're all in different direction. If they have the same magnitude, right, this one is basically going upward, vertically upward, right? Force 1 is going vertically upward, and force 2 is going vertically downward, right? They're completely in the opposite direction, but with the same magnitude. What does it mean? This force and this force, force 1 and force 2, they cancel out each other. Okay, so now, look. Force 3 is going to the right. And it has the same magnitude as force 4, right? Okay, but they're in the opposite direction. So what does it mean? That means force 3 and force 4, they cancel out each other. But anyway, let's write it in vector, right? Because they are vector. How do you see it as vector now? If force 1 has the same magnitude as force 2, but opposite direction. Apparently force 1 is like upward is a positive direction and downward is a negative direction. So we can say that force 2 is equal to negative force 1, right? Because negative means opposite direction, right? It's the same magnitude, but opposite direction. So I can say that force 2 is the same as negative force 1. Now, look at the force 3 here. It has the same magnitude as force 4. I mean, they all have the same magnitude, but let's say we'll only look at these two right now, right? But they're in the opposite direction. So what does it mean? Well, it means that, right, I can say that, okay, so on the right side should be positive, and on the left side direction should be negative, right? So I can say that force 4 is basically the opposite direction of force 3. Okay. As you can see here, right, they have the same magnitude, but they're in the opposite direction. They're going to the opposite direction. So I can say it like that. Okay. So now, what is the sum of all these forces? How do you write this, right? So the net force, right? Basically the sum of all these forces. I can say that it's the sum of all these forces, right? Sum of all these forces, right? Is basically F1, right? Force 1 plus force 2 plus force 3 plus force 4. Okay, so let me separate this. Okay, now, how can you rewrite this? Now you can see that. Okay, we keep force 1 as force 1 plus, what's force 2? We say it's negative force 1, right? So negative force 1, right? Plus force 3, we keep force 3 the same, right? What's force 4? We say it's negative force 3, right? Yes. Now, when you do this, right? This and this cancel out, and this cancel out. So what do we have, right? It cancel out, so 0 plus 0 equal to 0. So the net force here is 0, right? As you can see, the net force here is acting on this object here is 0. So as I mentioned here, basically, the object is not accelerating, right? When the net force is 0. Now, again, just to clarify, when the net force is 0, it doesn't mean the object is just not moving. It's not at rest. It could be moving at a constant velocity. Because in order for the force to act on the object, and when the force is acting on the object should be accelerating. So when the object is moving at a constant velocity, it's not accelerating. So that means the net force is 0 on the object. But if the object is accelerating, then the net force is not 0. Right? Basically, when I say net force again, it's just sum of all the forces. Right? Sum of all the forces here acting on the object. Okay. So next, let's talk about different types of forces. So what's the first type that I want to talk about is gravity force. Or force of gravity. Let's denote this as F with a subscript G, right? G stands for gravity. But what is gravity force, right? Let's say there's an object here, right? It's dropping, it's like it's falling, okay? So the object is falling, okay? Yeah. So of course, when it's falling, why is the object falling? Because the object is being pulled by the gravity. Okay, let me write it like that, right? Let me draw a straight arrow, right? So it's pulling by the gravity force, right? Now we're on the earth. There is gravity pulling on the object. That's why we are able to stand on the ground. Otherwise, we will be floating like the astronaut in the space, right? Okay, so what is a gravity force, right? We can say that, okay, let's say, okay, so gravity, right, is usually 9.8 meters per second square, right? So it's approximate, right? It's approximate. And if you want to write in a direction way, which is acceleration downward, right? So it's acceleration, right? It's negative 9.8 meters per second square. Now let's look at this, right? This is approximate value, right? So what does it mean, right? Acceleration? Well, like I said, right? In order for a force to exist, right? That means the object must be accelerating already if there's a force applying on the object, right? So this is accelerating downward. So with a negative, right? Because downward direction is negative direction. So it's going downward. What does this mean? Now think about it like that, right? You can see this as acceleration is negative 9.8 meters, right? Meters per second, okay? So you can see like this. Let me write it better. So negative 9.8 meters per second, right? That's what it means. Meters per second squared. It's meters per second. What does it mean? Right? It's acceleration. That means the object is accelerating at the 9.8 meters every second downward. So that means the velocity of the object dropping, like moving downward, is increased by 9.8 meters every second. So basically, when something is falling from the sky, or let's say something is falling in the air, it's not falling at a constant velocity. It's falling at a constant acceleration of 9.8 meters per second. So every second it increase the velocity of dropping, every second increase by 9.8 meters. So that is the force of gravity. Of course, when the object is falling, of course the object is falling from the air. So that's definitely some air resistant acting here. We call this drag force, right? Called D, drag force. Basically air resistance. Okay. Notice that I purposely draw the arrow of the air resistance shorter than the arrow of the gravity force, because when an object is dropping, like if you put an object in the air and let it go, right, the air resistance is not going to be large enough to push the object upward instead of having the object falling downward. The object will always fall downward because the gravity is larger than the magnitude of the gravity is larger than the magnitude of the air resistance, right, the drag force. Okay, next, the second type of force I want to talk about is normal force. Okay, we can denote this as n, right, with the head here. So we know that it's a vector because it's a force, right? And force is a vector. But even if you want to write like this, I guess it's fine, right? Just make sure that the n looks like a subscript. Maybe like this, right? Yeah. Okay, so what is a normal force? So now let's talk about an object, right? So this is an object. And you have a table here. The object is just on top of a table. Okay, let me draw it. Okay, like that. Right, so that is a table. So that's the object. Right, so that's the object. Okay, so what is the normal force acting on this object? Well, because this object is not hanging in the air, it's not dropping in the air, so there is a table, basically the table here is exerting a force upward onto this object the moment this object is being put here, right? So there's a force acting upward like this, right? And it's the normal force. right? So basically the table is exerting a normal force on the object. So I can say that the table is exerting a normal force on the object. Okay, and you can see that obviously the object is also being pulled by the gravity, so that is actually sitting on the table. Otherwise, it will be flowing around. Okay, so this is normal force acting on an object that's lying on the flat surface, right? So because this is horizontal surface, it's flat. Now we have to think about another situation, right? Let's say there's a ram here, like this. Right? There's an object here. Okay, so here's the thing. The object is sitting on the ram. Okay, so let me just label this. That's a ram. That's the object. Okay, so we know that the ram is still exerting a normal force on the object. So here, let me write it here. The ram is exerting a normal force on the object. However, at this time, you have to account for the angle of inclination, right? Because it's not on the flat surface here, right? It's not flat, it's slanted, okay? So it's a different scenario, right? This is on the flat surface, but this is on a slanted surface. But still, right? The ram is also applying a normal force on the object here. Okay. The third force I want to talk about is the tension force. Right? We can denote this as, right, T, and then with the head here. So it's a vector, right? Force is a vector. Or if you want to write it like this, that's fine too, right? F subscript T, right? That's a tension force. We can see it that way, right? We understand that. Okay, so what is a tension force? Now think about that. You have an object here, right? That's being hanged by a string or a rope, right? So let's call this rope or string, right? This. And of course, right? The rope or the string is exerting a tension force on the object, pulling upward, right? So we can call this the tension force, right? Going up, right? Because it's pulling upward. It's pulling upward. And of course, right? Even though right, it's pulling upward, there's also a gravity force here. Right? There's a gravity force here too, right? That's pulling the object down. Well, you can see that assuming that, okay, the object is at the same position, hanging there, right? It's not moving. Then the force of tension is the same as the force of gravity, but they're in the opposite direction. So the magnitude of the tension force and the magnitude of the gravity force will be the same, but they're just in the opposite direction, right? Yeah. Okay. So that's one situation. Right. Second situation here, right? Let's say there's an object here. And that is a surface here, okay? So you attach a rope or a string here, right? Okay, let me make it thick, right? So this is rope or string, right? This one here. Okay, so it's pulling this way. So where's the tension force? It's going to the right, right? So we know that the tension force is here. So the tension force is going this way, right? But it's horizontal, right? It's flat, so that's it, right? It's going to the right. However, in this situation here, let's say here, so we will attach a rope here like that. pulling like this. Rope or string. Like this, right? And of course, right, the tension is going this way, right? But we have to account for the angle of inclination. Like for example here, right? Like the angle of inclination. It's just not flat, right? It's pulling this way. But still, there's a tension force here. Okay, next. The fourth force I want to talk about is the friction force. In friction force, right? There are actually two types of friction force. One is called static friction force, one is called kinetic friction force. So we would denote static friction force as, right, F subscript S, right? So that's static friction. And F subscript K is kinetic friction. Okay, so what is static friction and what is kinetic friction? Well, let's talk about static friction first, right? So we have, okay, this. Let's say an object is on a ramp, right? It's sitting on a ramp. Okay, so that's a ramp and that's an object. Okay, if, like, look at this, right? There's a slope on the ramp, right? It's inclined. And if I look at this picture, you can imagine that this object should be falling down, should be sliding down like that, right? But if it's not sliding down, right? Then why is it not sliding down? Right? Let's say object at rest. Here, okay? Why is it not sliding down? Because in order to keep the object to be at rest here, not sliding down, there must be a force of friction. There must be a friction force here, right? That's keeping the object on the ramp. Somewhere here, right? Somewhere here, right? There must be a friction here. And that is called a static friction because the object is not moving, right? It's just the object being at rest and the friction force is trying to keep the object in the same position at rest. So that it's not sliding down. Now, let's talk about the kinetic friction, right? F subscript K. Now, let's say there's an object here now. Right? And the object is actually moving. And what is stopping the object moving, right? Let's say this is a rough surface, right? So this is like a rough, okay? Like the surface is rough, okay? And that's something that's like sort of like impacting the object when it's trying to move this way, right? To the right. And on the surface, it's a rough surface, but this is acting to kind of affecting the object moving to the right, slowing down or whatever. And that force is the friction, right? It's kinetic friction because it's a friction force here that's affecting the object moving to the right. So that's kinetic friction because the object is moving. It's not at rest. It's not sitting there. It's actually moving, right? So that's kinetic friction. So that's the difference between static friction and the kinetic friction. Okay. The fifth type of force I want to talk about, right? It is called the drag force, right? And drag force, it can be in fluid or in the air, right? And that is called the air resistance, right? In the air. Okay, so how do we denote drag force? Let's just denote it as like capital letter D with a head on it, because force again is a vector. Okay, so what is a force? Let's talk about force in the air, right? Like air resistance. Let's talk about air resistance. When an object is falling, right, it's pulled by the force of gravity, and of course there are also drag force acting upward, right, which is air resistance, because the object is in the air, as I mentioned before. Okay, now what if you flow an object? Let's say you flow an object, right? It's flow, right, in a projectile motion. And if the air is blowing this way, right, blowing this way, the air is blowing this way, of course the object here will be experiencing the air resistance here, right? So air resistance. And it will slow down the object from moving to that direction. It's also called a drag force, right? So that's the air resistance force. That's the air resistance. It's also called a drag force. And of course, right, in the fluid, as you can see, fluid, if some object trying to move in the fluid, of course the action or their motion will be slowed down, or maybe it's even hard, right? Because fluid has some sort of density there, right? It's a lot harder to move in fluid than to move in the air. We're all moving in the air, and it's okay actually, unless the wind is really harsh and it's really like difficult for people to move forward, I guess. Okay. And of course, we have other forces, right? So other forces like spring force, um, thrust force. So when a rocket setting off, and then electric and magnetic force. But I will not talk about this force in detail right now. Okay, now next, let's try to practice identifying all the forces, right? Identify all the forces acting on the below object. So example 1, I guess. So this one is a free fall of an object. Now, of course, when the object is falling, there must be force of gravity here, right, acting to pull the object down. Because, like, if we're within that region, we're still within the gravity region, right? It will be pulling down. And of course, right, the object is falling in the air, and of course, there must be air resistance acting upward as it's falling, right? Because it's falling to the downward direction, the air resistance will be upward, will be acting on the opposite direction. So this is a drag force. Are there any other forces applying there on the object? Is it any force moving to the left or right? No. Right? Okay, so I guess that's it. Okay, next. Second example. Let's say there's an object, right, being hanged by a rope, right? So this is a rope or a string. Like this one. So of course, right, there's a tension force pulling upward, right? Upward. But since the object is actually at rest here, it's not really moving in different position, it's also being pulled by the force of gravity. Well, if not, then the object will be flowing around, right? It will not just stay here. It's because it's balanced by these two forces, right? The magnitude of the tension force and the magnitude of the gravity force are the same, but in the opposite direction. That's why they net out, right? If you sum up this force, the net force is 0, so the object is just staying here. Okay. Third example. Say there's an object sitting on the table. So identify all the forces acting on this object. Of course, right, the table is exerting a normal force upward to hold the object there. So we can say that, okay, so there is a normal force, right? Yes. But of course, right, the object is being pulled by the gravity downward. So there's a gravity force. In order to balance this object to stay in the same position, otherwise the object would be going upward already, right? If there's no gravity, then there's only one force pushing it up, then it's going to go upward. But it's not, right? It's staying on the table. It's not moving. It's at rest. Of course, there's a force of gravity acting here, downward. However, is there any force pushing the object left or right? No, that's none, because the object is not even moving, right? Left or right, and it's not going up and down, right? So the force of the normal force has the same magnitude as the gravity force, and when you sum up the force together, right, the net force is 0, right? So it's not moving. Okay, so the fourth example here. Let's say there's an object here. Right? So there's a rope that's pulling, okay? Rope or string that's pulling this way. And this is a rough surface, okay? So this surface is rough surface. So basically, when I say rough surface, right, you can imagine that this is not ice, okay? It will be a rough surface. So when you're pulling, of course, right, there's a tension force here, right, pulling this way. But of course, right, if it's a rough surface, when you're pulling the object, it's not really that easy, right? So what is stopping it, or what is impacting it, right, affecting it, slowing it down? It is the friction force, right? So that is a friction, and it's kinetic friction because the object is moving, right? It's not staying still, it's moving. Okay, so that these two forces here. And of course, you can also see that, okay, sure, there must be a normal force of the floor acting, and then a gravity force like acting down here, right? Right, so this is a normal force, the ground is acting, the surface is acting up on the object, right? And of course, right, the gravity force is pulling the object down, right? So that it stays there. But if you add up these four forces, so all these forces here, right, whether it's 0 or not, I don't know. But if this object is moving at the constant acceleration, I mean, let's say if this object is accelerating, then there's a force going this way, right? So the net force is not 0. But if this object is moving at a constant velocity, then the net force is 0, right? So I can say that here, if the object is accelerating, right, then the net force is not 0. But if it's moving at a constant velocity, then the net force is 0. Okay. So now, the next thing I'm going to talk about is Newton's law of motion. Okay, so the first Newton's law of motion is that, right? When the object at rest, staying at rest, or the object is moving, continues to move at a constant velocity, only if, right, if and only if the net force acting on the object is 0. So let me write that down. An object at rest stays at rest, or an object is moving, continues to move at a constant velocity. Then, if and only if the net force, right, acting on the object is 0. Okay, so this is going back to what I talked about at the beginning. Now imagine, right? This is an object. Let's say all forces have the same magnitude and they're going into like direction like this. The object should be around, like, should be still, right? So the object at rest will stay at rest. I mean, it could be moving, right? Because the force, that's force only if there's acceleration. If there's no acceleration, even if they're moving at a constant velocity, the force here will still cancel each other. So coming back here, pay attention to this line here. An object is moving, continues to move at a constant velocity, then if only if the net force acting on the object is 0. Now, notice that the word, right? Constant velocity. Like I said before, right? If the object is not moving at a constant acceleration, or it's not moving at acceleration, there's no force, right? So that's why the net force acting on the object is 0 if the object is only moving at a constant velocity and it's not accelerating. Okay, now, why? Well, let's come to Newton's second law of motion, right? And what is the second law of motion telling you? Simply, F equals ma. And notice that, right? F is a force, and force is a vector. Mass is a scalar, so it doesn't have a head here. Acceleration is a vector. It has a direction and a magnitude, so it has a head here. Now, what does it mean? Well, it means force equals to mass times acceleration. Right, so these are what this letter stands for. Okay, so next question is, what is a mass? Okay, so what is a mass? Actually, mass is quantity of matter in an object, or in human as well, right? The thing is, how in real life, right? Have you ever asked a question, okay, what's your mass? Or will you ask, what is your weight? So let's talk about this, right? Mass versus weight. So what's the difference between these two? Right? Because in real life, we never ask people, okay, what's your mass? We always ask them, what's your weight? So now, the weight is simply the mass of an object being pulled by the gravity. So you can say that, okay, it's the mass, right? It's being pulled by the gravity. So that means the mass of an object is just the quantity of matter in that object. It doesn't factor into the gravity. But the weight is basically the mass of the object being pulled by the gravity. Okay, now, how are you able to measure the mass of an object then? Because everything on the earth, is being pulled by the gravity. So you are basically measuring the weight of the object, not the mass of the object. Well, that is a device to measure the mass of the object, right? So it's a balance. So we can say that a balance, you have to use a balance, right? Measures the mass of an object. And how do you measure the weight of the object? You use a scale. A scale measures the weight of an object. Okay, now we do know that what are the variables in this equation here, right? F equals ma. So now let's talk about why this equation makes sense. Let's rearrange this, right? We have this, right? F equals to ma. Let's divide both sides by m, right? So let me put it here. Okay, so we have acceleration equal to force divided by m. Now think about that, right? A constant force applied on an object will make the object move at a constant acceleration. And we do know that the larger the force applied to the acceleration, the larger the force applied to an object, the larger the acceleration of the object is. The smaller amount of force applied to the object, less acceleration the object will have, right? So for the force, if it goes up, right, of course acceleration goes up, right? And if the force is lower, then acceleration will be lower. It's positively correlated, right? Now, how about the mass, right, of the object? Well, when you apply the same amount of force on a larger mass, right? So let's say the mass is large. Well, of course, the acceleration will be lower, right? Because the larger the mass, you need a larger force. Right? We're holding force constant here. Okay, so now, what if the mass is smaller of an object? You apply the same amount of force on the smaller object. Of course, the object will move faster, right? So it will accelerate faster, right? So it's negatively correlated here. Now you see that it makes sense, right? Yes. Then all we need to do is just multiply both sides by m. We have this equation back, right? Force equal to ma, right? Force equal to mass times acceleration, okay? Now again, right? In order to have force, you have to have acceleration. The object has to be accelerating. Or if we apply a force to an object and the force is not zero, and the object must be accelerating, right? So it's not moving at a constant velocity. It's accelerating. Okay, so that's the Newton's second law of motion. Now, what is Newton's third law of motion? It's basically called, well, we can simplify it, right? To say that it's action-reaction. Action-reaction. What does it mean? So that means, right, when two objects are exerting force onto each other, they have the equal magnitude of forces, but in the opposite direction. So let's imagine this, right? This is a wall. This is a wall. So we call this wall, right? It's a wall. Let me make it thicker, right? So that it looks like a wall, right? And you push the wall with your hand. So you're pushing the wall, right, with your hand. So you're pushing it, okay? So that's your hand. You're pushing the wall. When you push the wall, your hand is exerting force onto the wall. So here, right? Force of hand on wall, right? You're applying a force on the wall. But at the same time, the wall is also applying a force onto your hand in the opposite direction. So here, but with the same magnitude. So this is, okay, so I should put the head here, right? So, right, force of wall on the hand, right? So with the same magnitude, opposite direction, right? So, I mean, in this situation, the wall is not moving. You are not moving, even if you're pushing the wall, right? Well, we know that because the wall is fixed there, right? You are not able to actually move the wall by just pushing it. But the wall will not move either, so the wall is not going to push you to a different position, going like backward or anything like that. So both you and the wall will stay in the same position, right? So that also explains, okay, why the net force here would cancel out each other. The net force here is 0, really, right? The sum of all this force would be 0 because they're same magnitude but the opposite direction. Okay, hope you enjoyed this video. Don't forget to subscribe to my channel. Thank you.